In this lecture, we'll start talking about an important quantum algorithm known as quantum Fourier transform. So far we've developed quite a bit of technology working with quantum circuits. We've seen them as as methods of transforming an incoming quantum state into an outcoming quantum state. So they encode some kind of unitary transformation on a state that lives in the Hilbert space of n qubits. That's a 2 to the n dimensional space. But so far we haven't talked about how we do computation with it. How do we map a computational problem into a quantum unitary transformation? So a very important application is known as the quantum Fourier transform. So let's just review what a Fourier transform is. So it's a classical operation. And it's a discrete as opposed to a continuous Fourier transform. So just view this as some mathematics problem that we want to solve. So suppose I have a list of n real numbers, or actually we can have complex numbers. They don't have to be real. So suppose we have a list of n complex numbers. And let's call them x0, x1, up to xn minus 1. So a Fourier transform takes this list of n numbers and generates another list of n numbers. So that's input. And the output is, let's say, another list of numbers. Let's call them y naught up to y n minus 1. According to this equation. So we're saying yk is 1 over square root n. There are different conventions about where you put that, but let's put it here. Then sum over j equals 0 to n minus 1 of xj times e to the 2 pi I, so I is square root of minus 1, jk over n. Okay. So we're summing over j here, and the exponent, if I call like 2 pi k over n, let's call it alpha for different k. For each k, this is essentially doing this. N minus 1. So alpha is something proportional to k, and then we have the exponential of alpha times j. So this is kind of a discrete version of maybe the Fourier integral transformations that you might have seen. So we multiply, let's say, f of x by e to the I kx, integrate over x to find some function of k. Here, j really labels like the position. So instead of integrating over x, we sum over j. So we sum over a discrete set of points, and for each of them, multiply that by e to the I j, this distance, times something that's proportional to this number k. Okay, so let's do, for example, if n is equal to let's say 3. So what are these things? So let's say why not? So let's do an example, just explicitly writing out the sum to get better intuition. So this would be 1 over square root 3 sum over j equals 0 to 2 xj, and then alpha in that case is just 0 because k is 0. So that's it. So this would be 1 over square root 3 x naught plus x1 plus x2. What about y1? It's going to be 1 over square root 3. Now, each of them multiplies. So my alpha is going to be 2 pi over 3. So it's going to be x naught times 1 again, j is 0, plus x1 e to the now j is 1, so it's going to be 2 pi I over 3 plus x2 e to the 4 pi I over 3. And finally, y2 will be so now for 2, this becomes 4 pi over 3, k is equal to 2. So it's going to be x1 e to the 4 pi plus x2 e to the 8 pi. So each of the y's is going to be some linear combination of the x's, and the coefficients are determined by these exponential factors. So if you want to do this on a classical computer, well, how would you do it? Well, I guess you can just directly calculate it, put a for loop that calculates each of the y's individually. And then to calculate each of the y's, we need to calculate like n terms and add them up. So it seems that the number of operations in this will go as like n squared. There are actually better algorithms like known as the fast Fourier transform that can do it faster. So, but even that doesn't go like n squared, goes like n times log of n or something like that. So if n is large, right, this algorithm can take a long time to calculate these classes. So let's see how we can construct a quantum circuit that would do this computation. So somehow transform the set of all x's to a set of all y's according to this this formula here. Okay. So the way we can think about it is to think of a change of basis with similar coefficients. So now suppose I have a set of basis states. Let's call them J equals 0 to n minus 1. So for example, if you have 2 qubits, J will take 4 values. In general, if you have n qubits, it's going to be 2 to the n different values. So it's going to be 0, 0. Maybe we call that just state 0. Then it's 0, 1. Let's call that state 1. There's 1, 0, we can call that state 2, and there's 1, 1 that we call state 3. So we have a bunch of states. You can think about them as states in the computational basis, or in general, we have a bunch of basis states. And then consider a unitary transformation that does this. That takes J and transforms it to 1 over square root n times sum over k equals 0 to n minus 1 of e to the 2 pi I j k over n times k. Okay. So now if I send in some wave function, let's say input state. So there's going to be some quantum circuit that does this. Then if you input, let's say, a superposition, sum over j equals 0 to n minus 1, xj, now those numbers become the amplitudes times j. Let's see what this goes to. So this will go to sum over j, then I have the 1 over square root n. I have the xj. And now each of the j's becomes a sum over k e to the 2 pi I j k over n state k. Now let me switch the order of the sums. The sum of a sum, it doesn't matter in what order we sum. So this becomes sum over k equals 0 to n minus 1. 1 over square root n, that's just a constant. Now let's do the sum over j. And then I have xj e to the 2 pi I j k. And then k doesn't depend on j, so I can put this in parentheses and have a state k there. So this whole thing is just a Fourier transform of xj, right? That's yk over n here. So this machine sends sum over j sends this to sum over k yk k, right? So you put the numbers you want to Fourier transform as the amplitudes of some incoming state, each multiplying one of the basis states. You send it into this machine, it performs a unitary transformation, and out comes a state where the amplitudes are the y's, are the Fourier transform of the list of xj's. All right, it may not be obvious at this point why this transformation is unitary, so let's try to explicitly see why this particular transformation is a unitary transformation. So suppose these basis vectors are orthonormal, so the set of, let's say, k's in that expression, and then we're going to generate for each j, right? We're going to generate this superposition given here. So if we can show that all of these superpositions are orthonormal, if the k's are orthonormal, then we've shown that the transformation is unitary. So it doesn't change the normalization, and it just generates another orthonormal basis. So let's consider J1 to be so showing unitarity. This is a dummy summation variable, but let me just call it K1. And then I will have e to the 2 pi I J1 K1 over N. Basis vector K1. And consider J2 sum over K2. 2 pi I J2 K2 over N K2. So now if I want to take the inner product of J1, J2, I need to take the conjugate of, let's say, one of them, of J1. So to take that conjugate, I write it as 1 over square root N. Sum over K1 equals 0 to N minus 1. And then I have to change the I to minus I. So this becomes into the minus 2 pi I J1 K1 over N. And then I have to take the conjugate of this basis state. So from this, I can write J1, J2. I multiply this sum and that sum. So I give the factor 1 over N, get a sum over K1, and a sum over K2. And what remains is, well, I need to multiply the argument. So it's going to be e to the 2 pi I over N. And then I have J2 K2 minus J1 K1. And then we have this inner product K1 K2 here. So this is going to be delta K1 K2, right? They're orthonormal. So if K1 and K2 are different, this is 0. If they're the same, that's 1. So from here, I obtain that J1, J2 is equal to 1 over N. Then I just have sum over K, right? So K2 must be equal to K1. So let's call it K. There's going to be only one term, right? So suppose I'm doing the sum over K2, then for each of the K1s, there's only one value of K2 equal to K1 where this term is not 0. So that reduces the double sum to a single sum. And then here I get into the 2 pi I over N, J2 minus J1 times K. So these are the same, so I factor that. Okay. So now, well, what is this thing? So this looks like a geometric series, right? So e to the 2 pi I over N J2 minus J1 K is, we can call it like beta to the power K, where beta is just this. So then this sum, so sum over K equals 0 to N minus 1 of beta to the power K is going to be, that's an identity. It's going to be 1 minus beta to the power K over 1 minus beta. So one easy way to verify this is to just multiply both sides by 1 minus beta. And from this, we'll see that. So let's do an example for n equal 4, for example. So if I have k equals 0 gives me 1 plus beta squared plus beta cubed. That's n minus 1. So this times 1 minus beta, I'm going to get all of the terms minus. So 1 times that gives me all the terms. Then I get minus beta times that, which essentially shifts the exponents by 1. So 1 times beta becomes beta, beta times beta becomes beta squared, beta squared becomes beta cubed, and beta cubed becomes beta to the 4th. So we see these terms cancel 1 by 1. So the only things that remain are 1 and minus beta to the 4th. So, and in general, we can show that in the same way. So then we find that sum over k equals 0 to n minus 1, beta to the power k is 1 minus, let's see what beta was. It was that thing over here. So it's two pi I j2 minus j1 times n. Oops, this is n, sorry. This is the last exponent. So if this runs to n minus 1 here, I get the n. In the same way that this ran to 3 and I got minus 4 here. So then I have a factor of n here. And then I have to divide that by 1 minus e to the 2 pi I and j2 minus j1. So that's just e to the, yeah, that's just beta. So then we'll see what happens. So if j1 is not equal to j2, then in the numerator, I get 1 minus e to the 2 pi I j2 minus j1. So some integer factor of 2 pi, and that's 1. So this is 0. So the numerator is 0, and then it's divided by the denominator. It gives me 0. The reason I said j1 not equal to j2 is that when j1 is equal to j2, the denominator also becomes 0. So we're dividing 0 by 0, and it's kind of tricky. But then in that case, it's clear what the sum is, because each of these will be e to the 0. So each of them will be 1. And then when I sum the ones, I have n terms. So I get n over n, and I get 1. So essentially what we did, we showed that J1, J2 is equal to delta J1, J2. Is 0 when they're different, and it's 1 when they're the same. So this change of basis does not change the orthonormality, and then it's a unitary transformation. Okay, so let's keep pushing this. So now my goal is to construct a circuit that does this, that performs this transformation on all the basis states. Okay, so in order to do that, let's introduce a little bit of notation. So first, if we're working with a quantum system, n must be 2 to the n, right? Because we always have a certain number of qubits, so then the dimension of the vector is going to be 2 to the n. So this works only for n's that are 2 to some integer power. And then I can just do the representation. So I can imagine, for example, if you have 3 qubits, let's say 0, 0, 0, I call it 0, 0, 0, 1, I call it 1, 0, 1, 0, I call it 2, 0, 1, 1, I call it 3, 1, 0, 0, 4, 1, 1, 1, 0, 1, 5, 1, 1, 0, 6, 1, 1, 1, 7. So this is just like, these are the state of individual qubits. That's some label we give to the entire basis state for a bunch of qubits. And it's easy to see that this is just, so if you think of this as some bit string, this is just a binary representation of that number. So 7 would be 1, which is 1 times 2 to the power 0, plus 2, which is 2 to the power 1, plus 4, which is 2 to the power 2. So then we have this notation that J, which labels the state, we can represent it essentially as a binary bit string. Like that, there's this mapping between them. And J, if you think about what it is J1, 2 to the n minus 1, plus J2, 2 to the n minus 2, goes all the way to Jn, 2 to the power 0. It's also useful to introduce a decimal notation. So in the same way that we say like 0.1 is 1 times 10 to the minus 1, we can also play a game like this. We can say 0.j1, or let's say jl plus 1 up to jm is going to be, that's shorthand for jl. Now it's going to be 2 to the minus 1 plus jl plus 1, 2 to the minus 2, plus all the way to jm. So here we have to add, so 2 to the minus, I guess, m minus l. And I believe I need a plus 1 here. Right, so if m is l plus 1, yeah, if m is l plus 1, m minus l becomes 1, and then I have to add another 1 to get this 2, for example. So that works, plus 1 here. Okay, so that's a useful notation. So now let's try to represent the Fourier transform in a different way that allows us to construct a circuit that would perform the unitary transformation. So that's one notation for standard binary representation that labels the states. And then this is like a decimal binary notation. All right, so I claim that, let's write this. So we're saying J goes to sum over K. And note that n is 2 to the n. So we're now thinking about a system of n qubits. So these basis states are the basis states for little n number of qubits. So then this goes to e to the 2 pi I j k over n k 1 over square root. So writing this in a different notation, if we think about the states of qubits now, instead of just this label, so J1 up to Jn goes to 2 to the little n, sum over k equals 0 to 2 to the little n minus 1, e to the 2 pi I. And here I have this notation, this binary representation J1 to Jn. K has a binary representation K1 to Kn. This whole thing is divided by 2 to the n. And that multiplies a vector K1 Kn. So K1 Kn, now we can view that as a tensor product of a bunch of single qubit states. This looks like a minus. This is actually a set of dots. So this is just a binary representation there. So there's a very nice way to write this. So I write it and then I'll try to prove that it works. So this I can write as 0. So 0, let's say I have qubit 1, qubit 2 up to qubit little n. So in this order, the first one, let's say, corresponds to qubit 1. Point Jn 1. So point Jn just means Jn over 2. Then the next one, so these are tensor products if you wish. The next one is 0. 2 pi I. Now I have point Jn minus 1 Jn 1. So this means again Jn over 2 plus Jn minus 1 over 2 plus Jn over 4. And then we can keep going doing these tensor products, and the last one is going to be 0 plus e to the 2 pi I point. So if the last one is for qubit, this is for 1, this is for 2, the last one is going to be for n. This is going to be J1 here. Every time I subtract the 1 from the first guy. Up to J. And then the whole thing is divided by 2 to the n over 2. So that's the claim. I haven't proved it yet. So let's maybe do an example here to just verify this before a formal proof. So how about we do that for 2 qubits to see what things look like. So let's do example with 2 qubits. So 2 qubits, the states are going to be 0, 0, 0, 1, 1, 0, 1, 1. This is 0, 1, 2, and 3. So let's try to construct that. So we're saying now n is little n is equal to 2. So I would have 1 to the 2 to the power of 1, so n over 2. Then this first state is going to be 0 plus e to the 2 pi I. Then I have I have Jn, so let's say yeah, so n is 2, so that's J2. So this is J1, J2 is equal to that. Can be either 0, 0, 0, 1. J2 over 2, right? That's what this means. 1. And then the next one is going to be 0. Now here I get J1 over 2 plus J2 over 4 times 1. And that's it. So this is going to be 1/2. I have 0, 0, taking the tensor product of this with that. The 0, 1 term gives me the 1, 0 term, taking 1 and 0 from here gives me, so this is continued over here. That gives me e to the 2 pi I just J2 over 2. That's 1, 0. And finally, I have e to the 2 pi I J1 over 2 plus J2 over 3/4, like 1/2 plus 1/4, or J2 times 3/4. So let's write that in the regular notation. So capital N is 4, right? So I can take out a fact. So let's write this. So this is 1/2. 0, 0 is just a state 0 in this different, in the J notation. Plus for the state 1, this guy, I can write it as e to the 2 pi I over 4. And then I have I have 2J1 plus J2. For the next guy, which is this one, I have e to the 2 pi I over 4, and then I get 2J2. Now I play a trick. If I add a 4J1 here, I'm not going to change anything because 4 cancels this 4. J1 is an integer, so e to the 2 pi times an integer is 1, so that's not going to change anything. So that's to say 2, 1, 0. Finally, I have, let's do this over here, e to the 2 pi I over 4. I have 2J1 plus 3J2. Again, I add a 4J1 to this. which doesn't change anything because 4 cancels this 4. I get an integer multiple of 2 pi, state 3. So lo and behold, that this is a standard Fourier transform that we were talking about. So that's 1 over, say, square root 4, right? Have a 4-dimensional space, and I have a 0 plus e to the 2 pi I over 4, capital N is 4, 2j1 plus j2 is just a j, right? The binary representation of j is j1, j2, so j is j2, j1 plus j2. Then the next one is e to the 2 pi I over 4. And then here I have 2 times j. So now this is the k equal 2 term, which multiplies 2. And finally, I have e to the 2 pi I over 4, 3j, right? So this is 3j2 plus 6j1. So it's 3 times 2j1 plus j2. So that's 3j. And that multiplies state 3. So in this particular example, we just saw explicitly that this kind of tensor product with this structure works and produces the Fourier transform. So let's now prove this in general. So I want to write that the above product is the Fourier transform. So let's look at it. So I have 2 to the n over 2. Then there's a sum k equal 0 to 2n minus 1. So 2 to the n plays the role of capital N. That's a number of states, that's the dimension of the Hilbert space. Then I have e to the 2 pi I j k over 2 to the n times k. So that's the Fourier transform. Now, I want to write this. I write my k as the string k1, k2 up to kn. And I write my k over 2 to the n. I write it as a sum. So let's do this here. So I have 2 to the n over 2. Then I have a sum over, let's say, k1 is 0 to 1. k2 is 0 to 1. kn is 0 to 1. So each of them can take 2 possibilities. That gives me 2 to the n different possibilities. And here I write e to the 2 pi ij. So this k over 2 to the n, I write it as sum over L equal 1 to n of KL 2 to the power minus n. So again, and then here I have that k, I represent it as k1 up to kn. So where did that come from? Well, k is, according to our general binary decomposition, is k1 2 to the n minus 1 plus k2 2 to the n minus 2 plus ultimately kn 2 to the 0, or n minus n. So then k over 2 to the n is going to be k1 2 to the minus 1 plus k2 2 to the minus 2 plus kn 2 to the minus n. So that's precisely what this sum here represents. Okay, so that's an aside here. Just an aside to show that sum. So let's continue that sum. So therefore, we can write this expression 2 to the n over 2, sum over k equals 0, 2 to the n minus 1, e to the 2 pi I j k 2 to the n k. This now, the exponential of a sum, right, is a product of exponentials. So then I can take each of those with the associated k. So I can write this as 1, 2 to the n over 2, k1, k2, kn. And then let's just put this with it. So I have e to the 2 pi I j k1 over 2 k1. So now that gets tensored with e to the 2 pi I j k2 over 4, which is 2 to the 2 k2. And that keeps going. And finally, I tensor this with 2 pi I j kn two to the minus n kn. Very good. So now I have this product and I'm summing over all the k1, k2, and kn. So again, I can distribute these through. I can take each of the sums and apply to the place where I have k1. So if I have a sum over k1, I can just bring it over here because the rest of the stuff doesn't have a k1 in it. Sum over k2 similarly doesn't have any other k's in it. So this reduces to, if I do 0, I get 0 for that k. If I do 1, I get e to the 2 pi I j, and then k1 is 1, but then I have to divide it in this case by by 2 to the minus, divided by 2, so multiplied by 2 to the minus 1, and that's 1. Then this whole sum gets tensored with 0, 2 pi I j 2 to the minus 2. So this is for qubit 1, this is for qubit 2, and this keeps going and gets tensored ultimately with okay. So now let's try to connect this to the original product that we wrote. So essentially the exponent that appears here, say for qubit L, what is that exponent? Is e to the 2 pi I j 2 to the minus L. So now we're saying j is j1 2 to the n minus 1 plus j2 2 to the n minus 2 plus all the way to jn times 2 to the 0. So that's the expansion of j in terms of these bit strings as binary values. Now, if I divide that by 2 to the L, you will see what's happening, right? So essentially, if L is, let's say, less than one of these, so then I'm left with some integer. So if n minus 1 is, let's say, larger than L, what remains is j, which is some integer times some positive power of 2, which is again an integer, and e to the 2 pi I, an integer, is always 1. So those guys don't matter. So the only terms that matter is that if I get like a j divided by 2 or divided by 4, it's when that order is less than the j to the L. So that essentially gives me that tells me that e to the 2 pi I j 2 to the minus L is equal to e to the 2 pi I 0 is it j equal L or L plus 1 or L minus 1? Let's think a little bit about this. So what order gives me 1 over 2 when essentially so this is always there, right, for any of them. So that's why they always terminate at the last one. And here L is 1. I guess even the 2 doesn't matter. So it seems to me that yeah, so for the smallest L, very few matter. And for the largest, so it seems actually this should be n minus L plus 1. So let's scrutinize that a little bit to see where it starts. So suppose I divide that by 2 to the L, right? So the first term that doesn't matter where I get an integer is that so you suppose you have a j to the, I don't know, let's say j to the alpha times 2 to the n minus alpha divided by 2 to the L. So that's the boundary where this doesn't matter. So if n minus alpha is equal to L, or if it's larger than L, so larger than equal to L, then what remains is an integer. So So that means that alpha, in order to count this term, so alpha is really the index of j, right? When the exponent is 2 to the n minus alpha. So alpha must be smaller or larger. So this means it doesn't matter when alpha is smaller than or equal to n minus L. So when it does matter, when I have to keep it, is when alpha is larger than n minus L. So it starts from n minus L plus 1 and goes all the way to j. So that leaves me with the expression that we wrote initially. So when n is equal to 1, I start at when n is equal, L is equal to 1, alpha just becomes n, right? There's nothing else. And then when L is equal to 2, I get the next one. So that tensor is with so when L is equal to 2, I have n minus 1. And then this keeps going, and at the end of the day, we get when L is equal to n, this starts at 1. Okay, so I think that's a good place to stop. So we essentially map the Fourier transform into a particular tensor product. So then in the next lecture, we'll construct an explicit circuit using some control gates, some Hadamard gates to generate that state explicitly.